In 30 through 40, construct an algebraic proof for the given statement. Cite a property from Theorem 6.2.2 for every step. So we're going to be proving that for all sets A and B, A minus B intersection A intersection B is the empty set. Now, there are a lot of laws here, and chances are you're going to have to memorize all these laws. And I'll be honest, like some of these laws I don't know off the top of my head. That's because there's just so many of them. There's so many rules to memorize. So if you asked me to like recreate this list, I wouldn't be able to do it. Now we have to think about how to deconstruct this left-hand side so that it equals the right-hand side. And I think the first thing we should focus on is that set minus. There's a set difference law that tells us that A minus B equals A intersection B complement. Now, each time we simplify this left-hand side, we're going to need some law to justify our simplification. In this case, we're using the set difference law. Now we have a bunch of intersections. Everything is intersections here. There's no unions. Now, ideally, we're going to want to intersect this B complement with that B because there is no intersection between B and B complement. So ideally, we would like to move some of this stuff around. Now, what I'm thinking about utilizing is the associative law so that we can move these parentheses around. But we have to be careful because in the associative law, there's only one pair of parentheses, whereas in our current expression, there are two pairs of parentheses, which means that one of these pairs of parentheses is going to have to act as the C here. I don't think it's going to matter which one is our C, so I'm going to say this is the C in the formula. This is still going to be the A in the formula, and this is going to be the B in the formula. Now keep in mind, it's actually B complement, but the way that we apply this formula is by rearranging where these letters are. So right now we have A intersection B intersection C, and we want to rewrite this as A, which was also A, intersection, and then B intersection C, but our B here is actually B complement, and our C here that we're intersecting with is really A intersection B. Now, this step is justified by the associative laws. So we have to write out by the associative laws. Now from here, we're going to want to simplify inside of these parentheses. Again, the goal is to really group up this B complement with that B somehow. And so what I'm thinking about utilizing is the associative laws again, which says that we can rearrange the parentheses here. Now, in this case, we're actually going to be going from the right-hand side of this law, which is what the format is here. This is A intersection B intersection C. And keep in mind, the letters are not exactly the same, but in order to utilize this law, we have to figure out what is our A, what is our B, what is our C in the formula. Now, the next step is actually pretty tricky in my opinion. What we're going to do is we're going to swap these two. And you'll see why we swap these two later when we apply the associative law again with these two expressions. So I'm going to swap these two terms utilizing the commutative laws here. That's the first law. So we could say by the commutative laws. And then the reason we do this is because if we can use the associative laws again, we can move these parentheses to surround these two terms instead of just A and B. And that will allow us to unlock the empty set pretty soon. So now we're going to use the associative laws again. And so by the associative laws, we can move these parentheses over just a bit. And that's because both of these are intersections. And so that makes it easy to move parentheses around.